Alright, so we're going to talk about some physical properties of liquids now. We're going to open up by talking about vapor pressure and boiling point. And so we talked a little bit about vapor pressure, last week, and so let's build on that this week. And just a reminder of what it is. So molecules can exchange between liquid and gas phases. So evaporation. So liquids can evaporate. And when they do, these gas particles exert a pressure. And we call this pressure vapor pressure because it's the vapor of the liquid. And again, so this pressure is vapor pressure. So we'll draw a picture here. Maybe that'll help make it clear. Alright, so if we have a closed container, this is key because if it's not closed, stuff evaporates in the gas phase and it's gone. Alright? So, again, evaporation can occur below the boiling point. But if we have a container and it has particles that are in the liquid phase, well, every now and again, one of them will get enough energy and they'll pop in the gas phase as well. And so we have gas up here, liquid down here. And so these are very close together. So these are lots and lots and lots and lots and lots of particles in this area. Whereas these are spread out. There's lots of open space. These are very tightly packed together, right? Remember, liquids are very dense. There's just a few gas particles up here. And every now and again, a gas particle also can pop back in the liquid phase. And so you reach this kind of what we call equilibrium, where they're going in the gas phase as fast as they're returning, and so there's a certain number up here, a certain number down here. It might not be the exact same molecules all the time, but the numbers are the same. And so we have a pressure. These are exerting a pressure on the walls of the container. And we talked about last week, if we heat this up, then more particles have energy to jump into the gas phase, right? So the strong interactions, or strong interactions between molecules, I should say, so we have strong interactions in liquid phase. And if these are strong, attractive interactions, then it's harder to escape from your neighbor. So you need more energy. You need to be hotter to have a vapor pressure that's significant. Because otherwise they all just hang out down here and they just kind of hang around each other. They like being around each other, lots of attraction. So, to overcome this attraction, there has to be, enough energy to do that. You have to have enough kinetic energy. If they don't have enough kinetic energy, they don't escape. It's like having like an escape velocity. The rockets that we launch into space, well, gravity means that they're attracted to the Earth. That holds them down. And so you have to have enough force to get away. You have to establish enough kinetic energy to get off the surface of the Earth. And it's the same deal with these gas particles. They have to have enough kinetic energy to escape the surface of the liquid and go into the gas phase. So, increasing temperature equals an increase in kinetic energy, which equals greater number of particles with energy to escape. Okay, so, and by the way, you know, if it has higher kinetic energy, it's essentially the hot particles leaving into the gas phase. It's an interesting thought. And so it actually cools the liquid down. So evaporation cools the liquid. And so that is how something like a mister on a pool works. Is increases the surface area, there's more evaporation, that evaporation cools the water, so if you run it at night. So in addition to being cooled by the cool air at night, if you're trying to keep like a pool from getting hot in the summer here, you can do that. Or swamp coolers use this property to cool air, so the water evaporates and gets colder, and then it pulls in heat from the air, and then the air gets cooler, so you get more humid and cool air. Now, if you're in Florida, that evaporation doesn't go very well because their humidity can be like 100% like all the time. But here it works great because their humidity is like 0% all the time. So having a little extra water in the air is not necessarily a bad thing. Whereas in Florida, just evaporation is incredibly slowed. So, what else can we say? Oh, stronger IMFs. Stronger intermolecular forces. Right, that's the part we're talking about last week. So this is actually what we talked about last week. This is what we're talking about this week. So stronger intermolecular forces are going to equal a lower vapor pressure because they're being held back more strongly. You know, the stronger the attraction is down here, the harder it is for a molecule to make it up here. Okay. So it's harder for molecules to break free. Alright. And so as an example of this in action, let's compare. You know, if we have NH3 versus CH4, which has a higher vapor pressure at a given temperature? Assuming they're both, you know, not at their boiling point, because at their boiling point, they're both going to be atmospheric pressure. But if they're at a temperature where they're both liquid, which one would have a higher vapor pressure? And the answer is going to be the one with the weakest intermolecular forces. This one only has dispersion forces. This one has hydrogen bonding. So this has weaker intermolecular forces because it's a nonpolar molecule, and that's going to equal a higher vapor pressure. Alright, so that's an example of us applying this idea. Alright, so let's carry it forward to boiling point now. So, what is boiling point, right? So boiling point is when the vapor pressure equals atmospheric pressure and boiling occurs. You've probably seen water boil a million times. You might not have known that detail, but that's where the vapor pressure of the water equals the atmospheric pressure of the room. And it's also why water boils at lower and lower temperatures as you go up in elevation, because the atmospheric pressure is lower at elevation. So, let's get that written down, huh? So boiling point. This is the temperature where the vapor pressure equals the pressure of the atmosphere. And boiling occurs. Alright, so what does this mean? Well, stronger intermolecular forces equals a higher boiling point. You have to put more heat in to overcome the molecules holding it back. Well, more heat means higher temperature, and so the boiling occurs at a higher temperature, so stronger intermolecular forces. higher temperature for the boiling point, for all the reasons we talked about before. And again, as an example, in case you're curious, NH3 has a boiling point of negative 33.34 degrees Celsius. It was actually the first refrigerant for this reason. But it smells terrible, and it's denser than air, so people would have issues where they would suffocate, things like that, if their refrigerator sprung a leak. So, if that happened in their sleep, bad news. That said, large commercial units still use it. So, like, I lived down the street from an ice cream factory when I lived in Oregon. That's true, I did. And they had these massive freezer units because they had to freeze like an entire warehouse for storage. They had to freeze the ice cream, as they're making it. They have to, have all this refrigeration unit stuff, and ammonia was the refrigerant used in all of it. So, how does that compare to something like CH4? Well, you expect CH4 to have a higher or lower boiling point here. Let's start there. Well, these are going to have more attractive forces among each other than these do. Again, this is a small nonpolar molecule. So, it'll have dispersion forces only. Whereas this is hydrogen bonding. So this should have a higher boiling point than this because this has less intermolecular forces. And so, if we just look at the numbers, yeah, it's lower, alright. Negative 161.5 degrees. And, what about H2O? Well, it also hydrogen bonds, but it's better at hydrogen bonding than ammonia. And I bet you actually know the boiling point for this one pretty well. 100 degrees Celsius is what the scale is built on. So water has stronger intermolecular forces than both of these. It has a higher boiling point. So again, stronger intermolecular forces, higher boiling point, because you have to get the stuff hotter to have enough kinetic energy to more readily escape at a rate where vapor pressure equals atmospheric pressure. Alright, so that'll do it for these two properties. So next we're going to talk about viscosity and surface tension, and then we will be done talking about properties of liquids and attractive forces for this week. Next week we'll take the idea of these attractive forces or intermolecular forces and apply it to the idea of solids. So we'll go gas, liquid, solid. We are condensing this week, and then next week we'll freeze. We'll go to the solid phase. Alright, so viscosity and surface tension coming up next.